Multiprocessor behaviour, what can't you rely on? This is my title. If you take a typical multi-core system, like this phone here, you might think of it, we might draw a picture of the stack of the hardware and the software in the system. Something, oh, no, that doesn't work so well. Something like that. Yeah? Elegant picture, hardware, compilers, operating systems, applications, nice clean rectangular boxes with elegant edges and elegant pastel colours. I could stop there. So we have to remember the normal development process, which I imagine everyone here knows very, very well. So how many of you, just to give me a sense of the audience, how many of you are practicing engineers? Almost everybody. How many of you write concurrent code at least once a month? At least once a day? Okay. So you know this stuff, but maybe it's not as uppermost in your mind as it is normally. So when we're building systems, in normal practice, the only way that we have to assess whether they're any good is to execute them on some test cases. Right? We have this test and debug and hopefully fix cycle, in which we have some code which is executable and we have some tests with some manually specified outcomes for each of them. Somehow that might be specified as a checker or as a list of outcomes or something. And then sometimes we have some prose specification document. It might have some precise description of the syntax of whatever we're building, or the types or the API or what have you, but then a prose description of the behavior. And when we look at the architecture manuals for our processors, when we look at the programming language manuals, the ISO standards, the Java standard, this kind of thing, that's what we get. And we've had that for the last 50 years or so. We're accustomed to that being normal practice. But that prose description, when it comes to tricky things, especially these tricky multi-core behavior things, the prose is intrinsically ambiguous and incomplete, and very often just plain wrong. Right? And moreover, because it's prose, it's not a computational artifact, we can't use that in our testing-based development process in any direct way. So, in the light of this development method, and knowing that the systems that we construct are built by very smart people, highly educated, very ingenious, but subject to a bunch of constraints from the legacy standards that they're working with and subject to often market pressures, then this picture is not as accurate as it might be, and probably this picture is a better representation of what we have to deal with. And it's sometimes hard to pick out the abstraction boundaries in the systems that we build, but you can see here there's some kind of silicon stuff down here. And apologies to those that have seen some of these slides yesterday. There's a C compiler here with its different phases. There's a front end and some optimizations and a back end near the silicon. And in here somewhere there's a TCP stack and a JavaScript engine and a browser and yes, the software you use to do your banking transactions on the top. So what might we possibly do about that? All right. So each of these pieces is intimidatingly large from any kind of mathematical semantics point of view, which is where I came from into this area. You know, these are hundreds of millions of lines of code or hardware description or whatever. It's very difficult to do anything with them except execute them in that test and debug process. But the interfaces between them, they're still pretty intimidatingly large, but they're kind of stable, and they are just about within the capacity of a large academic research project to get to grips with them. So what we've been doing for the last several years is to try at each of these levels, at the multiprocessor concurrency level, at the C language level, also for linking, at some of these network protocols, to be precise about the allowable behavior. And in order for that to be useful, well, when we started, we thought, yes, we'll just pick up the ARM reference manual, and we'll read it very carefully, and we'll write down a little bit of honest mathematics, and then we'll start proving some correctness theorems and building model checkers and things for software. And that was a happy, happy, innocent world, because what actually happened is that you pick up any of these reference manuals or language standards. I don't want to pick out any particular one as being especially bad. You pick them up, and you read them very carefully, and you try to write down something mathematically precise, and as soon as you do, you come up against ambiguities and inconsistencies. And you go along to the vendor and you say, after you found the right people to ask, which can take a couple of years, you go along to the vendor and you say, do you mean this or this? And sometimes they say, oh yeah, we mean this. But quite often they say, that's a good question. So these precise definitions, they need to be constructed as part of this process, and that's really what we've been doing. So this is, at the moment, a big UK-funded project, RIMS, Rigorous Engineering of Mainstream Systems, with lots of people involved, but broadly parts of the Cambridge Systems and Security and Computer Architecture group, a bunch of semantics people, and some more semantics people in Imperial and Edinburgh. So the basic idea of all of this stuff is to see how we can replace those prose descriptions of subtle behavior by something rigorous, something that's precise, but still loose enough to accommodate the implementation variation that you actually have, something that's clear, and most importantly, something which is executable as a test oracle. So what do I mean by that? So this is not necessarily a specification which is executable in the conventional sense as a slow implementation, but a specification that gives you some way, given an observed behavior of the real system, to decide whether that is allowed or not. Right? Something which you can use as an oracle for the results of testing. And if you can do that, then your testing process is greatly simplified, because now you don't need to make up manually the intended result for any test. So that means you can randomly synthesize tests, or you can systematically synthesize tests. And we've depended on that a lot. And it also gives you a way to investigate what these legacy standards are. Right? You can have an experimental process in which you make some tests and build a model and compare the results of those in an automatic way, and then discuss the differences with the vendors, and then fix up the model or report the implementation bugs, depending, and then repeat. Right? So that's the process that we've been doing for the last few years. Okay, so now let me focus in on our proper subject, multi-core stuff. Right. So this is work with an overlapping bunch of people in roughly chronological order, starting with Susmit Sarkar and working up to Kindle Nienhuis for many years. So the basic question that we're asking here, the first question is why this microphone is falling off. And the answer is that it's designed for people without glasses. So what is memory? What is the abstraction of memory that programmers writing concurrent code would like to think in terms of? So computer memory is a very old idea. So here is part of the design of the analytical engine by Charles Babbage in the 1830s. And this is a sort of a top view of a machine. This is, in some sense, the CPU. Each of these circles is a stack of cogs, with one cog for each digit of a 50-digit number. And this thing over here is the store, which is a great long line of these stacks of cogs and some cute little gears that you can use to access individual memory. And you can see he had in his mind a clear division between the mill, in which the operations are performed, and the store. Moving ahead, 1945, this is the EDSAC, one of the first operational machines, this one from Cambridge. It had a processor and a memory, and life was good. 1962, this is the first multiprocessor that I found, the Burroughs D825. Outstanding features include truly modular hardware with parallel processing throughout. And you can see computer marketing has advanced little since 1962. So this was a machine then with, I think, 2 cores accessing the same memory. So how could that behave? So the simplest model you could possibly think of is that the threads are just doing reads and writes to that same shared memory. So this is the sequential consistency model. You interleave the operations of the threads in some arbitrary sequential order, and each read reads from the most recent write to that same location. So what we're going to do in this talk is look at some of the ways in which that is not the case. So we're going to do it with a series of little examples. So here's first example. It's a tiny, super naive mutual exclusion algorithm. So we've got 2 threads. On this thread, we write 1 to X, and then we check whether the other thread has written 1 to Y, and if not, we enter our critical section, and on this thread, we do the converse. So can they both be in the critical sections at the same time, I ask? And what I hope is that you will be sitting there thinking to yourself, at the same time? What does he mean by that? But let's see if this is at least in that sequential consistency model, right? If this can be the case. So let's first simplify the example a little bit. So I don't want to talk about critical sections or the notion of something being in a critical section, which is also a dubious notion. Let me just simplify down to the write and the read and ask a more concrete question. Can we reach the final state in which this is 0 and that's 0 in the same execution? Well, in that sequential consistency model, it's defined by considering the set of all of the interleavings of the individual threads. So we can write down all the interleavings of the individual threads. Here they are. So the nodes are states of the system, and the transitions are read and write actions. Right? And there are 6 of these interleavings, depending on what you do first. And you can see, it's very easy to see that you cannot possibly reach that final state. Okay, let's try it. Live demos are always good to add a little adrenaline to the process. So this is an x86 laptop. So I'm going to take that example and express it in x86 assembly code, pretty much, and compile that in a particular test harness and run it 1,000,000 times and look at the histogram of the final values of those 2 registers. So we see here that almost 500,000 times one of the threads went first, and almost 500,000 times the other thread went first, and very occasionally they were so precisely synchronized that both threads read 1, but quite often both threads read 0. So that's not a mutual exclusion algorithm that we want to use on this x86. It's not a mutual exclusion algorithm, indeed. So option 1, the hardware is busted. Perfectly possible. We have, in the course of this work, found quite a number of hardware bugs, which is a wonderful way of getting the attention of processor vendors. But what you do is you go and ask the architect, is this behavior intended to be allowed? And the definition of a computer architect is someone who has the societal authority to answer that question. Right? And in this case, they say that's supposed to be allowed. So option 2, the test is not the one that you thought you'd written, or the test infrastructure is broken. That happens too, but not here. And option 3, the model is wrong. Right? And indeed, SC is not a good model of any of these commonplace hardware architectures. So now we're kind of lost. We're floating in a vacuum of unknowingness. So what can we do? We can look at the implementation of the processor. Well, actually what we can do is look at a fuzzy JPEG of a die photo of the implementation of the processor, because that's the only information that we really have access to outside Intel. And if we were inside Intel, maybe we could look at 500 million lines of hardware description language, but we wouldn't really want to. All right? So there's lots of things going on in there. There's lots of highly devious hardware optimizations being produced by computer architects, which we don't want to think about. It's too complicated and also too confidential. But I can tell you that a good programmer abstraction for x86 is something a bit like this. So each of those hardware threads we can think of as not acting directly on the shared memory, but pushing its writes into a FIFO buffer of writes and reading, if it can, from that write buffer, and otherwise reading from that shared memory. All right? So I'm just plucking this out of thin air in order to save you the several years that it took us to go from that observational data to a shared understanding with various people that this is a good programmer's model. And now we can see, if we go back to that example, it's pretty easy to see how that final behavior is allowable in this model. So you can do that right and push that into the right buffer, and do that right and push that into the right buffer, and then both of these can read from the shared memory to read the initial state value of 0, and then the two writes can pop out of the right buffers and affect the shared memory. Right? So that buffering has the effect of a thread local reordering of reads and writes to different addresses. Not all of the phenomena that we're going to look at are thread local reorderings, but this one you can think of like that. Okay, a bit more x86 for a couple of minutes. So this is not a RISC processor. I'm not sure are there any RISC processors these days? No, not really. But it does, so in particular, it has a whole lot of instructions that both read and write memory. So you can do an increment instruction on two threads. And even in the SC model, these are not atomic actions. So that increment and that increment in parallel could perfectly well both read 0 and then write the same value if they're sufficiently well synchronized by happen chance. Yeah? So if you want to make those atomic in the x86 architecture, you can do so. You can stick on what is in fact a 1-byte prefix in the encoding, confusingly called a lock, because it isn't really a lock from a programmer's point of view. And that has the effect of making this increment atomic and forbidding that final state. Right? But it also has the effect of there's a bunch of other similar kind of instructions. It also has the effect of waiting for that buffer to flush. Okay. And the mfence instruction has a similar effect of waiting for the thread's own buffer to flush. No synchronization with any other threads. So now you know enough to understand the behavior of some simple concurrent algorithm. Let me just do a quick check. How many of you already knew this? Like quite a few of you. Oh, okay. Oh, sorry, I should have gone much faster. So now we can look at how we would implement a language level primitive lock. Right? So we're going to, in fact, take a particular Linux implementation of a spin lock and its corresponding unlock written in x86. Look something like this. So what we've got is a locked atomic decrement on the X, and then if the result is negative, that means we've succeeded in taking the lock, and we enter our critical section. And when we leave the critical section, we set the lock back to 1. If that fails, then we do a little spin, but we spin just trying to read, not trying to do this atomic decrement. So we spin reading until we might be able to get the lock, and then we go back to the beginning and try again. Yeah. So why is this good? Well, because this locked decrement waits for that buffer to flush, then by the time we have entered our critical section, that write of x of a negative value for x, sorry, a 0 or negative value for x, has been forced to be visible to all other threads. Right? So that's necessary. And indeed, then for the unlock, we don't wait for our buffer to flush, and that's fine. Why is that fine? It's fine because the effect of that write sitting in this thread's write buffer for an extra however many instructions, that effectively just means that this critical section is extended a little bit longer than it might have to be. Okay, so that was, you should be very suspicious, because that was a pretty hand-wavy argument. Right? But you can hopefully see that this model is giving you enough to informally reason about the behavior of code like this. And that is in contrast to the situation that the original authors of this code had. You can look back and see in the Linux kernel mailing list, which is a wonderful archive of argument, a very long thread back in 1999 in which people debated whether this was a correct single instruction or not for a couple of hundred messages. Right? It was an important deal because if you add in a fence or a locked instruction there, that was a significant performance hit for the entire kernel. They had no way to resolve that argument until they found a handy Intel architect who just pronounced to them ex cathedra, yes, it's fine, right? Because there was no reasonable model. So that was a hand-waving argument, but you can make this precise. So we have a mathematical model, in fact, in a couple of forms, which are proved equivalent in an automated reasoning tool, the Whole4 interactive theorem prover, and you can prove in that, and Scott Owens has done this, that several theorems, but the high-level one is that any program which is correctly using these spin locks, i.e. it has no data races that are not protected by this spin lock in any SC execution, any such program will behave as if it was in a sequentially consistent machine. Right. So that's very comforting. So let me now leave the happy, simple world of x86 and move on to the bleeding edge world of ARM processors and IBM Power processors, which are kind of similar to each other, although not as much as one might hope. ARMs you're all familiar with. The Power processors that we were looking at tend to be power server machines, but there are a bunch of others used for network processors and other things. So let's look at another classic concurrent programming idiom. So message passing. So here we have two threads, and on this thread we write some data, and you might think of that as a great big data structure, multi-word thing, and then you write a flag to say this data is available. And then you have some other thread which is maybe busy waiting, in a simple case, reading that flag until it sees that value, and then trying to read the data. And what you would like, as a programmer, is for that read to necessarily see that write, and all of it, not to see the initial state of data. Okay. So again, let me simplify the test. Let's get rid of that while loop and just look at a single run with two reads of y and x and ask whether the final state, whether it's possible to read 1 for that and 0 for that in the same execution. Okay. So in that x86 model, each thread's buffer is FIFO. So if the Y has propagated to the main memory, enough for thread 1 to see it, then the X must also have propagated to main memory. So on x86, this will just work with normal instructions. If we run that on a variety of Power or ARM machines, so these are the numbers of times that we see the 1-0 outcome out of some significantly large number of trials in a particular test harness. And we see this is observable really often, like 1 in 100 times. Very frequent. So why is that happening? So again, it's happening because of clever microarchitects. You have an out-of-order pipeline. So the writes might be executed out of order. The reads might be executed out of order, or at least might be satisfied out of order. On each thread, they're to different addresses. No reason not to interleave them. In the interconnect and the cache protocol, the writes might be propagated out of order. You might have one interconnect for even-numbered cache lines and another interconnect for odd-numbered cache lines, something like that. All manner of plausible optimizations. So the world has gone shaky, as you can see. So we have to model all of this stuff in some way. But again, we like to model the actual implementations as abstractly as we possibly can and still provide a programmer model in order to provide a programmer model that people can get their heads around without simultaneously being microarchitects. So for the pipeline, we have to model potentially a tree of instruction instances for each thread in which, because the processor, if that's a conditional branch, it might speculate down one of these paths before this or before some preceding things are committed. So it might read some of these things early, before the earlier instructions. So that's one explanation for the behavior of that MP test. If you want to strengthen things up, there are various ways you can do so in these processors. So you can add in some kind of strong memory barrier on both sides, on ARM a DMB, on Power a sync. So this is more than you need, but this is enough. If you look at the observable data for those variants of the test, you don't see that final outcome anymore. So that's good. Now so far I've only talked about things with 2 threads, and there is a world of difference between 1 thread and 2 threads, and another world of difference between 2 threads and more than 2 threads, and after that it all kind of stays the same, as far as we understand it. So let's take this message passing test again, without the barriers, and pull this write off to a 3rd thread over here somewhere. So we write X, we busy wait until we can see it, and then we write Y. We busy wait until we can see it, and then we read X. And we ask whether this has to see this write, or whether it can mistakenly read the initial state. So on x86, this would still be fine, without any further ado. On ARM and Power, it's clearly allowed, because these are to different addresses, and you could just thread locally reorder in thread 1 or thread 2, and that would be fine. So suppose now you add in some dependency. I don't have time to talk about this in much detail in this talk, but add in something that preserves local order within each of these threads. Okay, so then what can happen is that this can propagate to here, letting that write go ahead, and that write can propagate to here, letting that read go ahead, without that write having propagated to here. Okay. So these machines are not what you call multi-copy atomic. Right? So the fact that a write has become visible to some other thread does not imply that it's become visible to all other threads. So this is a fundamental difference to that x86 model that we saw. That's what that says. And then, so if you want to program an iterated message passing scenario like this, you need, therefore, more than just this prevention of local reordering. You need also a strong barrier here, and that barrier has to have, and the ARM and Power barriers do have, what's called a cumulativity property. Right? So an ARM DMB, let's say, put here, enforces the ordering not just of the things program order before it with the things program order after it, but also the things which this thread has read from before it and what this thread writes after it. All right? So that means that it enforces the ordering of those two as far as any other thread is concerned. Right? And that, again, makes the iterated message passing idiom work. That's what that says somewhere. So this is not nearly as precise a picture of ARM and Power as the previous picture of x86. This is more of a suggestive picture. You have to think of each of these threads as having some kind of local view of memory and of the writes and barriers propagating potentially separately to each other thread. Okay. So these are all things that you don't get. You do get some properties. Right? So you do get, as the architects solved the coherence problem, more or less in the 1990s, at least for each location in isolation, you can think of the machine as behaving in a sequentially consistent way. Right? So in any execution, for each location, the execution restricted just to those reads and writes. If you just ignore all of the other reads and writes, then there is a total order of all of those writes and reads in which all the reads read from the most recent writes. So in a simple hardware implementation, that coherence order is the order in which threads get ownership of that cache line. And in fancier hardware implementations, well, there's more going on, but that's the basic thing. Okay, so there's a lot of things that I have not talked about. So in Cambridge, I do a part of a master's course, and we take about 10 hours to go through all of these things in some reasonable level of detail. So I'm abstracting and ignoring vast swathes of stuff in this talk. So now, let me turn to the modeling process. So I've given you some hand-wavy descriptions of some particular behaviors on some particular litmus tests, and I've spoken in terms of propagation and cumulative barriers and coherence and such like, which a priori are not very solidly defined. So what we've been doing in these last 10 years is building a series of models in different styles by a long process of this experimental semantics of generating interesting test cases, doing experiments on actual hardware, talking with the architects about the intended behavior, checking our models against that experimental data, and from time to time reporting bugs in hardware, and quite frequently fixing up our models and developing them and changing them over time. Right? And this is still ongoing. So there's a sequence of papers which you can read if you have a spare couple of minutes. But let me turn back to the use of the models. Right? So one thing is to have a mathematical description on paper. And if that is clear enough, then we can also use that to give an intuition for how things work for practicing engineers. Another thing we'd like is for it to be precise enough to do mathematical proof about, but then first we want it to be executable in one of these forms as a test oracle. So we want to be able to explore the model exhaustively in order to compute the set of all allowed behaviors of each of these litmus tests, because that's what we can compare against the experimental data that we get from practice. We also want to be able to explore it interactively in order to understand what the model says for one of these litmus tests. And then, well, this exhaustive machinery, this is not going to scale terribly well, right? Because you get quite a lot of executions quite quickly. So for testing the behavior of slightly larger pieces of software, say for some lock-free concurrent algorithm, you might like to be able to run that algorithm not just on the implementation of that particular hardware with the particular scheduling you happen to get, but in some way which is semantically complete, which to take a pseudo-random execution in a system which is guaranteed, if you run it infinitely often, to be able to explore all of the architecture allowed behavior. Right? So as of a couple of months ago, we can do that now for small concurrent algorithms. Right? And our plan there is to be able to turn that into a usable exploration and debugging tool for actual software development. Right? So that's something that people have never had. Right? Architecture vendors have said, you must program to the architecture. And then they give you processor implementations which exhibit some particular behavior, some subset of the large envelope of behavior that that architecture allows, and you develop software by testing against that. Right? So this is a fundamental mismatch in the whole industry, right, which we're aiming here to close up a bit. So to put the models together into a usable tool, we needed to do some mathematical engineering, if you like. So we take models of the instruction set from IBM or for ARM, produced in various ways, and in fact we have now an arrangement to take some of their internal models and turn them into mathematical models and give them to the world. So we take those instruction set models and glue them onto the concurrency semantics that I've been talking about, and glue that onto a front end that can read these little litmus tests, and another front end, which we take from a different project that's modeling linking, that can read honest ELF binaries compiled in a suitable way, and glue all of that onto a user interface. So let's see that working. Okay, so I'm going to try this on a little litmus test. This is an instance of this message passing example again, with a write of some data, and then a strong barrier, and a write of a flag, and a read of the flag, and now a conditional test on that flag. So this is going to be a power version. This is the power assembly. We'll run this in this handy-dandy web interface. So this is our mathematical model compiled to OCaml, compiled to OCaml bytecode, compiled by JSOCaml to JavaScript, and running in the browser. So there's a bit of a chain there. What you see, if I go back a second, so you have an interface here in which you can either just type in a litmus test, or you can select one from a library that we have, or you can upload an ELF file, small one, and then you can say, oh, I want to explore that interactively in the model. And this now shows you a picture of the initial state of our model. I'm not going to describe it in great detail, but there's some stuff for the storage subsystem that models the coherence order commitments which have been made so far and the list of events that have been propagated to each thread. And there's some pipeline model for thread 0 and a pipeline model for thread 1. And then there are these green things which are the allowed transitions of our model. And we can click on them. So you can see here that those final two loads are both enabled right now in the initial state. I could do, well, actually, there are two versions, one on both of the speculative branches. So I can just satisfy both of those reads first. And then I could turn to thread 0 and I could commit these two just load immediate instructions. And then I could commit this first store. And after the first store, but not before, I could commit this strong barrier. And now I can't do anything here until I propagate that write to thread 1, the first write. And now I can propagate that barrier to thread 1, and then I have to do this, which I haven't talked about, and then I have to do this, which I haven't talked about, and now I can commit this second write. So you can see I've been forced by the barrier to commit those thread 1 writes in order, in program order, and also I've been forced to propagate them in order, because only now can I propagate this write to thread 1. And you may not have seen, but then when I did that, the value that I could read for that on thread 1 changed. Right? So now I can read from that second write, and indeed I have to read from that second write. And now I could commit these instructions in order. Right? So I interactively had an execution in which the second read of the second thread was satisfied early, and then everything else happened, and then everything was committed. Right? So that's showing you a programmer usable view of the fact that the hardware is allowing speculative execution past that conditional branch. Yeah. And you can do the other things also in that tool. You can do the interactive exploration and the exhaustive exploration, although doing the exhaustive exploration in the web interface via this compilation to JavaScript is not highly efficient, and I do not recommend it. Okay, so now let's lift our sights up to the high-level languages. Well, it's going to be a less happy story, I'm afraid. So we look at this kind of test, this message passing test again. So we know now, in SC, then if that sees 1, then this should print 1. And on x86, that's true if this was an assembly program, and on ARM and Power, that's false if this was an assembly program. What about in Java or C? Well, we would hope that its behavior is still reasonable, even if we put it in some bigger program context. So we just put in another read of data up front. It should be totally irrelevant, right? It's reading data into a different variable, should have nothing to do with it. Unfortunately, people in the world out there are too clever. Right? And now we face the cleverness of compiler writers. So compiler writers want to make things go fast. You want to make systems that go fast, yes? Yes? Otherwise, we wouldn't bother with any of this multi-core nonsense in the first place, and life would be good, yes? So compiler writers, they want to make things go fast. They say, oh, here are 2 reads of data. Why don't I have a common sub-expression elimination optimization in my compiler that will replace this second read of data by just a use of the register which I happen to know already holds the value which I'm looking for. Good idea. Well, good idea in a sequential context, but in the concurrent context, that amounts to reading this value early before that conditional. Yeah. So the program, the innocent high-level language programmer has to deal with effectively the implementation cleverness of the microarchitects and of the compiler writers. And many of these optimizations were introduced and people committed to having them back when we had basically single processor machines. Right? So it's a tough sell, I can tell you, to go to a compiler writer now and say, you're not allowed to do common sub-expression elimination. This does not fly. These are the options that we have again, and again, option 4 is the one that we have to use. So now we have a couple of historical tales for Java and C++. So for Java, there was some kind of initial memory model which quite a while ago now was shown to not be very good. All right? So smart people, Jeremy Manson and Bill Pugh and Srita Advi, embarked on a formal definition that was supposed to fix this. Right? It was supposed to ensure that any program that was race-free in a sequentially consistent semantics should behave as if the machine and the compiler were sequentially consistent. Right? So that's a relatively nice guarantee to give, right? Because in order to assess whether your program is race-free in a sequentially consistent model, well, you only have to think about all of the possible interleavings in the sequentially consistent model. It's not a terribly nice guarantee, because thinking about all of the possible interleavings of your non-trivial piece of code can become quite tiresome and indeed impractical, but it's still relatively nice. Goal 2, however, was that all programs, because Java was supposed to guarantee memory safety even for untrusted code, all programs were supposed to satisfy some basic safety properties, even if they had races in. And then goal 3, standard compiler optimizations were supposed to be sound. And these people, they thought they'd done that, and in some sense they got close, but actually no. So Jaroslav Sevcik and Dave Aspinall showed in 2008 some nice example, and Pietro Cianciarelli and his authors had something else. So you can easily construct an example which is optimized by hotspot into giving some extra behavior, and behavior which is not allowed by the JSR 133 model. Right? So at that point, you either have to say, hotspot authors, you're not allowed to do that optimization, or you have to change the model. That's where we're at still. Nobody has proposed a reasonable fix to that model so far. C and C++. So here we have a simpler problem in a sense, because here we're not aiming to guarantee any kind of safety guarantee for arbitrary C or C++ code, right? The C and C++ languages are littered with places where if the programmer does something that the standard doesn't like, then the compiler is allowed to rewrite the hard drive into alternating ones and zeros. So what you can say here is that for programs which are data race free in a sequentially consistent semantics, you get the sequentially consistent behavior. If you have a race on a normal access in the sequentially consistent semantics, in the C++ standard terms, you have undefined behavior, and the compiler is allowed to assume that that doesn't happen. Which means that your program may be miscompiled in any kind of arbitrary way. So that's not great from a programmer's point of view, because it's quite hard to know that you don't have any races, but it's not much worse than the rest of C and C++. Yeah? So you have that, but then also, because these are supposed to be languages in which you can write high-performance code, we add in, well, the designers, which was chiefly Hans Bohm and Srita Advi and a bunch of other people on the WG21 Concurrency Working Group, like these people and some others, you add in some low-level atomic operations with more relaxed atomics. Right? So you have normal nodes and stores, and then you have atomic operations, which are labeled either as this is supposed to be a sequentially consistent operation, or these are supposed to be release writes and acquire reads, if you want to do this kind of message passing idiom, or more relaxed atomics, which are supposed to be highly efficiently implementable with just machine loads and stores. Right? So the idea here is that you have a range of facilities, and most people should use only the SC atomics and be race-free, but if you're writing some fancy high-performance concurrent algorithm, then you might want to use these things. So they produced, so the C++ committee produced an informal spec, an informal prose spec in the normal style of the standard for this stuff. And Mark Batty and some of the rest of us went along and read that and tried to turn it into honest mathematics and discovered some problems in it. For example, the happens before relation could accidentally be a cyclic thing. And it's, so in relaxed memory, we're used to thinking about strange causality orders, but having a cyclic causality order is a bit much, even for us. So we found and fixed various problems there and had some quite detailed conversations with WG21, which resulted in them changing their draft both before and after the C++11 and then C11 standards came out. So the text in that standard and the mathematical model that Mark Vatty produced are basically in sync. Right? We couldn't get actual mathematics into the standard because, for social reasons, that would be a tough thing to do. But this is one of the first times, I think, that an industry language standard has had at least a piece of it precisely defined. Right? So that's good, and we're all very excited. But there are still some quite big outstanding problems. Right? So some of these were known about back in 2010, but we didn't really understand how serious they were. So it's very hard to define an envelope of allowed behavior that allows all of the optimizations that compilers actually do, and all of the behavior that we observe hardware does, and that architects say hardware should be allowed to do, and forbids crazy, stupid results of values just being synthesized out of thin air. All right? So implementations don't, on the whole, synthesize values out of thin air, at least for race-free code, but to define that boundary has proved technically highly challenging. So that was known to be an issue in that C11, C++11 standard, and Mark's formal model allows it, and it's not clear whether we have any very good way of disallowing it. Right? So that's a bit of a problem. And then we thought we had proved some soundness of compilation results. So for each of these C11 concurrency primitives, there's sort of a canonical proposed way to compile a release write in C11 to a memory access and a particular barrier on x86 or ARM or Power or MIPS or what have you. Right? But these hand proofs turned out, recently discovered, are not actually quite proofs. Right? And indeed, the soundness of the compilation, probably to get that, we probably have to change the C++ model again in some ways. And then there's various other issues. So there's some more papers. Time is pressing. So let me say that if you work on GPUs or high-performance computing machines with RDMA or what have you, or distributed systems with some shared databases, you get the same kind of things cropping up. Bit different, same kind of things. So, state of the art. Hardware models, pretty well understood, at least for user code. Some corners are still being debated. Language level models, so the Java one is really broken. Parts of the C++11 model are quite sensible, but there still are some of these major problems. Sorry. Stepping back to the beginning. So what is the fundamental problem that we're working with here? The fundamental problem is that people are inventing quite subtle abstractions which are insufficiently tested. And now by tested, I mean all of these things. Right? We would like one of these models to be mathematically well-defined, and you like tools to be able to explore it on examples, and you want it to be internally self-consistent, and you want it to actually match what is implemented, and to check that both by testing and by proof. And you like it to be comprehensible, and you like to have tools that let you write programs above the model, not above the particular implementation, as program writing is still going to be based on this test and debug and fix cycle for the foreseeable future for most code, and you like it to be implementable. And you want all of these things at once, right? And some of them are not easy to assess or provide. So the basic idea that we brought to the party is to have these rigorous definitions which are actually executable as test oracles in some way. And for some of these models, we're doing that by exhaustive exploration of the model, which works just well enough for these small litmus tests. But this general notion one can apply to in many, many other contexts. People don't often seem to do it, but it doesn't need any terribly fancy machinery. With that, I thank you for your attention, and that's the end.
Well, during your talk, somebody typed the question I had in my mind as well. So you're coming with the bad news. You're the meter maid that puts tickets on everybody's windshield. What should we do about this? Today, what are the problems that while we wait for your wonderful results to eventually come out? How can we use C and C++, and what fixes do we need right now?
So this is a fine question. And I wish I had a fine answer to go with it. You could just stop writing concurrent code. Your life would be better. So if one is within, so it may be that I exaggerate the pain more than necessary. It's not clear. So let me re-emphasize first that if one is within the simple but quite common domain of properly, conventionally locked code, and you have done that correctly, then most of these issues will not matter to you. Right? And you can go beyond that. So if you're in C, C++11, and you're using SC atomics alone, then you should be fine. If you're in C, C++11, and you're using this release acquire idiom for message passing, that should be fine. Things become more tricky and delicate if you're using the relaxed atomics, and especially if you're mixing the relaxed atomics with SC atomics on the same locations, which people apparently do, but not that many people, then you may not be fine.
So before we go to the next question on the screen, so of course, raise your hand, and you can ask real-time questions here as well with your voice. So the next one that came up here was the security question. So how can these problems that you have explored, how can that be exploited by security hacks?
So that is another fine question, and we've been sort of vaguely looking for such instances because they would be wonderful marketing and grant funding tools. We've not really found them for this concurrency model stuff. Right? So you get strange behavior, and we can exhibit it in litmus tests, but in litmus tests, we're pounding on the machine, repeating the same test again and again and again. All right? So it's not very easy to turn that into an exploit. If you look at problems that we see in linking or in the C semantics, then there really are security problems. Do we know how to fix the Java language model? No. Nobody knows that. If you can figure that out, you can be famous and rich. Well, if you can figure that out, you're smart enough to become famous and rich, somehow. What happens with concurrency semantics in an environment line virtual machines, Intel VTX, etc.? Excellent question. I encourage you to find out. Yeah.
Any questions from the floor?
Be bold.
Okay, so with that, I'd like to thank Peter for this excellent talk. Thank you.
Okay, thank you. Thank you.